Okay, well, welcome to video 2 for the week. This will be start picking up from where we left off in chapter 1, and we'll see how far we can get in the allotted time. Again, it's going to be divided up into 3 portions just so that each video won't be ridiculously large. Otherwise, they might take a long time to load before they start playing. So there will be 3 parts to this, as usual, each of them about 25 minutes long. Where we left off was in the idea of dimensional analysis, and also remember that for the first chapter, the subjects may be a little out of order compared to our current textbook, because I'm actually using the lecture notes from the last textbook. And it's the same stuff, it's just a slightly different order. So anyway, this is the point where the first textbook covered dimensional analysis, and the second textbook covers it also, and then the second textbook goes into quite a bit of detail on it. And I think this is one area where we can kind of skim over things. I don't emphasize dimensional analysis as such to the same extent the book does. I tend to emphasize more making sure that the final units for a problem come out to be the way, come out to be the units that you want. Anyway, dimensional analysis is useful, though, to the extent that we can use it. And it is certainly important to keep your eye on the units whenever you're doing calculations that involve measurements. In this case, for dimensional analysis, the word dimension refers to the type of measurement. So for instance, length or distance versus volume or versus mass. Those would be different dimensions or different types of measurements. Units tend to go with the type of measurement, but they're not exactly the same thing as dimensions. So when I'm teaching calculations, I tend to emphasize units, whereas the textbook seems to want to emphasize dimensions, but it's really the same idea. In the book, they use square brackets to represent the type of measurement. And so remember that type of measurement is just another way of saying dimension, or vice versa. So for instance, the variable x usually represents distance. So the dimension would be considered length. And the symbol for a dimension of length in dimensional analysis would be L in square brackets. V, lowercase v anyway, usually represents velocity. Which is calculated as distance divided by time, which would be in dimensional analysis represented as L in square brackets over T in square brackets. L being length and T being time. So there's your dimensional analysis for that. A usually represents acceleration, and that is change in velocity over time. And in terms of dimensions, that would be, well, velocity is L over T. And that's divided by T again. And so that would be L over T squared in terms of dimensional analysis. So the symbols used for dimensional analysis for the types of measurements, or the dimensions in this case, would be for distance or length, L in square brackets, capital L that is. Area, as I mentioned before when we were going over the SI units, area in chemistry and physics anyway is treated as if it's length times width. And both of those are measurements of L, or length, represented by L. So the dimensional representation for area would be L squared. And volume is considered to be length times width times height, or treated as if it were length times width times height anyway. And that's L to the third power. Velocity would be L over T. Acceleration would be L over T squared. And energy would be, oh yeah, and I forgot to mention, mass is M in brackets, and time, oh sorry, not square brackets here, is T in square brackets. Or sorry, not volume. So energy would be mass times length squared over time squared. This would be the dimensional analysis type units for those kinds of things. The reason that we're looking at this really is, though, just to make sure that the quantities that we're using in equations are correct relative to one another, that they have the right dimensions, or the right units, in other words, relative to each other. So for example, for the equation x equals x original plus velocity times time, and then we have x, which represents position or distance. So I'm going to call it distance, is equal to the original distance plus velocity times time. And in terms of dimensions, if you look at the dimensions of distance, that would be represented by capital L in square brackets. And the original distance would also be represented by capital L in square brackets, because it's a distance also. Velocity is represented as distance, which is capital L, over time. And time is just time. Notice, though, that when you take L over T times T, the T's cancel out, and you end up with L, L, and L as the dimensions for every term in that equation. So they all have the same dimensions, and that's something that is required whenever you're adding or subtracting. So all terms have to have the same dimensions if you're adding or subtracting. Notice we multiplied volume or velocity times time here. Those two terms, because they're being multiplied, they don't have to have the same dimensions. the dimensions of the term overall after you multiply it out will be just whatever it works out to be once you've canceled out things that cancel out and multiplied other things together. So L over T times T is just L. And so that's the result there. But then when you go to add it to X original, that is also an L, and that's good because, like I said, if it's addition or subtraction, then all the terms have to have the same dimension. Another way to look at it is with units, and in fact, I prefer to look at units because units are more specific. There are ways that you can go wrong by looking at an equation like this in terms of dimensions. For instance, you could make sure that all of the terms in the equation have units of length, but what if those are different units of length? What if X original is given in meters and this V times T comes out to be centimeters? Well, you can't add those together. They have to be the same units. So when you go to units, when you look at units instead of dimensions, units are more specific. And by making sure the units are the same for addition and subtraction, you can make sure that you're right. So say if the units for X are in meters and the units for X original are in meters, then the velocity is going to need to be meters per second and the time can be seconds. If you've got, say, meters per second and the time is in minutes, then obviously that's not going to work out because seconds and seconds won't cancel. You'll end up with meters times minutes divided by seconds, which cannot be added to meters. But here, if you got meters per second and time in the same units, then seconds cancel and you get meters, meters, and meters, and now you can add them together. Okay, so that works out correctly. For a somewhat longer equation, X equals X original plus the original velocity times time plus 1/2 acceleration times time squared. Okay, you can look at that and make sure that you have the same dimensions. So in terms of dimensions, X, again, is a position or a distance, so that would be units of length. X original is also a distance or a position, so that would be units of length, plus velocity, which is units of length or distance divided by time, times time, which is units of time, plus 1/2. Now the 1/2 is just a number, so if you're checking for dimensions, the 1/2 has no effect on the dimensions. So you don't have to worry about that. Acceleration, though, is units of length or distance divided by units of time squared. And that's acceleration right there. And we're multiplying that by time squared. Okay, so if you look at how these dimensions work out, you've got length equals length. Okay, so far so good. Plus length over times time. So time cancels out. So far you've got length equals length plus length. That's so far so good. Now we've got length over time squared times time squared. That cancels too. So we've got length equals length plus length plus length. The dimensions work out. For units, again, we can be even more specific with units to make sure that things are really going to work out. The standard unit for length or distance would be meters, and the same for X original. For velocity, the standard unit would be meters per second, and for time, the units would be seconds. The standard units for, well, no units for 1/2 again, because that's just a number. But for acceleration, the units would be meters per second squared, and then time squared would be seconds squared. So again, seconds cancel with seconds, seconds squared cancel with seconds squared, and you have some number in meters will be equal to a number in meters plus another number in meters plus another number in meters. So that works out too. Remember that the bit about the dimensions or the units all having to be the same only applies to addition and subtraction. If you're multiplying or dividing, then you just do the same thing with the units that you're doing with the numbers. If you have, seconds times seconds, then you have seconds squared, for instance. Okay, so I think that's about all we need for dimensional analysis. I haven't really assigned any homework problems from that section in the back of the chapter because, and I haven't posted the homework on D2L yet, so I will do that very soon. I haven't assigned many or any, I don't think, problems from that section because the book goes pretty deeply into dimensional analysis, and I don't think we really need to go that far. Anyway, something else we need to cover is reviews of things like significant figures. Significant figures, or significant digits as it's sometimes called, is about the accuracy with which we know measurements. So the fact is that anytime you do a measurement of any kind, there is a limit to the accuracy with which you can know that measurement. That accuracy can be limited by things like the divisions on the measuring device, the quality of the measuring device, how carefully you're using it, the sharpness of your eyesight, all kinds of different things. But anyway, we can never know any measurement with total accuracy. In other words, there's always some uncertainty. And because of that, we need to limit, or actually we don't need to limit, the accuracy with which we can possibly know the result of a calculation is actually limited by the accuracy with which we know the measurements that go into that calculation. In practice, what we need to do is express the answers from calculations in ways that don't imply that we know the answer more accurately than we really do. Okay, so the uncertainty is indicated by the number of significant figures in a measurement. Generally, more significant figures would mean less uncertainty, and fewer significant figures would mean more uncertainty. And again, one obvious way that one obvious factor that would have to do with the number of significant figures would be how small are the markings on the measuring device. If you're measuring something like the width of this paper with a ruler, and you've got a ruler that's marked off only in, say, inches, with no markings in between the inches, then you're going to get a reading for the width of the paper that might have 2 digits in it. You'll be able to say the number of inches, and then maybe you can guess at the tenths of an inch beyond that. But that would be it. On the other hand, if you have a ruler that has lots of little markings in it, say a ruler that has, we'll go decimal here and say we've got rulers that are marked to the nearest hundredth of an inch, then you can have a lot more digits in your answer, because you're going to know how many inches the paper is, and you're going to know how many tenths of inches beyond that, and you're going to know how many hundredths of inches beyond that, and maybe you can even estimate to the nearest thousandth of an inch beyond that. And that means more digits, and that means less uncertainty. Generally, we consider the significant figures to be the digits known with certainty. That is not estimated. Our usual practice is that you usually take a measurement by reading the measuring device to the smallest marked divisions. And estimate one place beyond that. So for instance, if you're using like a standard metric ruler where the smallest markings are millimeters, then what you would do is you would measure the object to the nearest millimeter. And then read to the nearest tenth of a millimeter, and then estimate to the nearest tenth of a millimeter. And because of that custom, we normally assume that in any given measurement, that all of the digits are known with certainty, but that the last one is uncertain. And we assume that the last digit is uncertain to a degree of ±1, because, well, we want to leave a little room for error and disagreement. You're estimating that last digit. Basically, you're estimating how far the sheet of paper comes between one marking and the next marking. And, different people might see it differently. So, one person might say it's 0.3 and another person might say it's 0.4. And, so that allows us to be a little bit uncertain. Okay. But for the magnitudes of the units that are actually marked, you can read those with certainty. And we'll go over this in the lab in more detail when we can actually do hands-on work with that kind of thing. So if you're not quite getting it now, don't worry, we'll get to it in lab before long. Okay, so the first thing, actually, one other thing that you can do with significant figures is use them when doing calculations to, as I was saying before, prevent yourself from presenting an answer that implies greater accuracy than you really have. Okay, so the idea of using significant figures in calculations is that we don't want to imply that we know an answer more accurately than we really do. Or in other words, the accuracy with which you know the measurements that go into a calculation will limit the accuracy with which you can possibly know the result of that calculation. If you've got two numbers, say a calculation that involves three numbers, and two of those numbers you know with really great accuracy, and the third number you don't know very accurately, and you multiply those numbers together, well, the result is going to be something that you don't know very accurately because one of the numbers that went into it wasn't known very accurately. The problem is your calculator doesn't know anything about significant figures, and your calculator will often spit out numbers with a huge number of digits in them, even though there's no way you could possibly know the number with that much accuracy. So we have to be aware of the concept of significant figures and how to determine how many you're allowed to use in a calculation, mostly because your calculator is not aware of that. Okay, I see we're up to about 25 minutes, so I'm going to take a break there, and we'll be back in a moment.